I've just uploaded lecture notes on ion implantation on eLearn. So if you have time, we'll probably continue with implantation today. So let's see. Right, can you see the notes on the screen? Right. Okay. So let's continue. So we stop here. We discuss about the doping process and then the profile that we will have. Hold on, the profile that we'll have on the surface of the wafer, on the surface of the silicon, when you dope your dopants, right? So either it's p-type or n-type. So if your wafer is p-type, then to form a p-n junction, you need to dope a very thin layer of n. Can be phosphorus, can be arsenic, can be antimony, and it will take a profile like this. Okay, and the junction depth of the p-n junction is then determined by the intersection between the two profiles. Okay, so this is the profile of your dopant, and x0 here is, oh sorry, x0 here is the surface of the wafer, if you like here. Okay, z0 is there, and then the profile is going into the silicon. So I have to flip silicon now. So bulk concentration here is the background doping of the silicon, right? So from Czochralski process, for example. So in this case, the wafer doping is 1015. Maksudnya kita dope dia dengan, say if it's p-type, then we dope it with boron with 10 to the 15 per centimeter cube during Czochralski process in the molten silicon. And then the intersection between the profile and the background concentration or the bulk concentration is somewhere around 1.5, 1.6 micron. So therefore, in this case, the junction depth xj is about 1.5 or 1.6 micron. So if you put this into the wafer, so if your wafer is p-type silicon, so then you diffuse. So that means this depth will be around 1.5 micron. So this is n-type silicon, right? Made of phosphorus, for example. Okay, so that's how you form. So dopant type we've discussed in 386 last time. So since we are using silicon as the host, silicon is from group 14, okay, group 4. So if you want to have n-type doping, so you need to use the dopants from group 15. Okay, so it can be phosphorus, arsenic, antimony. So typically phosphorus, because they have one extra electron, so that will not be bonded to the silicon, because silicon has 4 bonds. Okay, so the fifth electron will be free, wandering around the lattice and conduct electricity as n-type. On the other hand, if you want to dope the silicon to be p-type, you can use boron, aluminum, gallium, typically boron. So it has 1 vacancy. Okay, so ada 3 valence electron, and silicon has 4. So then you generate 1 hole. Okay, hole is absence of electron. So wandering around the lattice, giving p-type conduction. So that's how you generate p-type, n-type. That's what we discussed last time in 386. So 2 types of impurities in silicon. The moment you incorporate foreign atoms into silicon lattice, they can either be considered as substitutional impurities or interstitial impurities. So impurities, if you recall, we learned in 386, impurities can either be desired impurities or undesired impurities. Desired impurities are the impurities that we incorporate as dopants in order to alter the conductivity of the silicon. Okay, so on the other hand, if you talk about undesired impurities, they can be metals or oxygen or carbon. They are not intended to be in the lattice, because of their presence will represent as defect or trap states in the band gap. Okay, shallow state or deep level state, as we discussed in trade 6. So if you incorporate say boron or phosphorus, so they will considered as substitutional impurities or dopants: arsenic, aluminium, gallium, antimony, germanium. So they are substitutional, okay, in nature. On the other hand, if you have oxygen, gold, iron, copper, nickel, zinc, magnesium, they are considered as interstitial impurities. Okay. So for substitutional impurity atom diffusion by direct exchange, so it will exchange the original atom, okay, by vacancy, by exchange and vacancy exchange. Okay, process B is more likely due to lower energy required. So vacancy exchange is more required, more likely to happen when you incorporate substitutional impurities like the one above, right? So you can see the position of the atoms. On the other hand, if you talk about interstitial incorporation of the impurities like oxygen, gold, iron, and others, so there will be hold on. Okay, they will form an interstitial on the side of the atom. Okay, sorry, interstitial. So silicon interstitial atom displaces a substitution impurity, driving it to an interstitial site. So on the sides, where it fuses to some distance before it returns to a substitutional site. So it stays on the sides. Okay. So that's how interstitial impurities are present in the lattice. So doping can be done by two approaches mainly. So the first one is by doping, by diffusion. So you can diffuse, we discussed in the previous class, you can diffuse your atoms into the silicon. Silicon diffuse means it goes into silicon to form a junction. For example, if your wafer is p-type, then you're going to end up with n-type. Then you will have your p-n junction. Okay. On the other hand, you can also ion implant. You can also implant at high energy. You want to see later on, you can embed the impurities, the dopants into the silicon at certain depth, specific depth. Okay, in order to design your junction in a specific way. Okay, so in the fabs, in the wafer fab, normally we use combinations of the above. Okay, we use in some condition, in some layers, use diffusion, in some other conditions, use implantation. So that means we combine both methods in order to realize the doping of the silicon at different level with different junction depth and architecture. So let's have a look at the difference between both. So if you look at diffusion, the one on the top, okay, so diffusion is what will produce is a process that will produce maximum concentration at the surface. Maksudnya, because you incorporate your dopants, say through the surface, so that will give you, say, x0 surface. Tengok ni dia punya ln of concentration against depth. Kita flip the axis. You can see that it takes that kind of profile for this kind of junction. Katalah ni p-type, then your dopants n-type, then you will have your peak concentration or max concentration at the surface. So normally we call this as n0. N0. Then as you go into the depth of silicon, then you're going to have a function of nx equals to blah blah. Okay. But the surface temperature, the surface concentration is called n0. Dopants diffuse into the wafer, right? Diffusivity of phosphorus, diffusivity of boron that we discussed last time in phase 6. So it's going to diffuse into the silicon, taking that profile. On the other hand, if you use ion implantation, kita akan pakai high energy dopant ions embedded or bombarded to the surface of the silicon. You can see the distribution of the profile of the implanted junction, if you like. So p-type, n-type, the bezels it is more in control. It's more square shape lah, if you like, yeah, at the bezels gate. But then you have a better control over the profile. It's not that distributed as what you can see for diffusion. Okay, it's more in control lah. Dia lagi narrow lah, because you are bombarded at a specific location on the wafer or into the wafer. Dopants embedded below the surface due to the high energy of the process. They are bombarded, then it can be embedded, and as a result, you will not have a peak concentration at the surface because of the nature of the process. There can either some depth, they can peak at some depth into the silicon. Okay, x, say x equal x1, for example. So the profile be slightly different and more in control, more narrower. Okay, so that's the difference. Right, some common dopant sources for n-type. If you want to incorporate antimony, for example, then typically we use antimony trioxide in the solid form, Sb2O3, arsenic, As2O3, arsine in the gas form, AsH3, phosphorus can be in oxychloride form, POCl3, POCl, we discussed last time, in liquid form, where you can bubble the POCl. Pentoxide, phosphorus pentoxide, P2O5 in solid form, or phosphine, pH3. Maksudnya you can use either, for example, if you want to incorporate phosphorus, it can be the raw material, it can be in the form of liquid, POCl, solid, PO2O5, gas, phosphine. Maknanya you boleh ambil one of these forms in order to incorporate your phosphorus into the silicon. So it's kind of flexible in that sense. So on the p-type, boron, you can have a very different choices. In liquid form, you can use BBr3, boron tribromide, solid B2O3, gas, one common one, bidibrane B2H6, trichloride BCl3, boron nitride Bn, solid. Okay, so we have range of different choices. So if you talk about POCl, for example, POCl dalam bentuk liquid kan, okay, liquid for n-type phosphorus. So what you have to do is just a simple furnace setup. So you have your furnace here. So heater dia, just to heat up, say to temperature of 1000 degrees C, for example. Okay, then you have your wafers there, vertically mounted. You can see the video I uploaded on Elan. Example dekat Yunus Nabil tu dia punya triple stack furnace. Dia ada all automated. So POCl setup. So you have your liquid open source to be POCl, and then you have nitrogen to be the carrier gas to bubble the POCl into vapor. Then N2 tu dia akan hantar the vapor into the furnace and to dope the silicon, right? So the moment you dope in this type of open tube diffusion, katalah you vertically mount your silicon like that in your furnace, and your POCl coming in, your vapor comes in. Okay, as a result of this, you will actually dope the whole surfaces of the wafer. Maksudnya kalau you punya wafer p-type here, so then you will diffuse a very thin layer of n-type on all surfaces, on the sides, at the back, on the sides, at the front. Okay, so you cannot choose only one specific surface because the process is run in a furnace, enclosed furnace, and you have POCl coming in. Okay, but the whole chamber will be filled with POCl punya material for the diffusion. Okay, the same goes to the back wafers as well. Semua ni entire. So then how do you remove the unwanted n-type on the side and the back? Okay, So here the process that we call PSG removal, phosphosilicate glass removal. After the diffusion, a diffusion will generate PSG. Bukan PSG Paris Saint-Germain PSG juga tu tapi two different things. Phosphosilicate glass, phosphosilicate glass PSG has to be removed after the diffusion. Kena remove PSG, kena buat PSG removal on the unwanted areas, side and at the back. For example, since you want to dope only on the front side, you have to do PSG removal to remove. So one example by Tempress. So this is the furnace that we're talking about. Furnace, you just imagine this is only one tube. So on this furnace Tempress, you have 3 stack. Ada satu stack atas, satu stack sini, satu stack. So you can actually accommodate 3 tube. So it looks like it can accommodate 4, tapi dia tak install kot. So you can actually have 4 tubes to hold the wafers. Wafer boleh masuk sini ya. Let me wafers. So this is the Tempress diffusion furnace that you can use to run the doping process. Right, let's have a look at the theoretical side of the process. Diffusion obeys a fixed first law, okay? Fixed law. Fixed law. Okay? So if you can recall, we learned about this in oxidation as well last time, where particle flux J is proportional to the negative of the gradient of particle concentration. So J equals negative D, diffusivity, dn dx, n is your concentration, D is the diffusion coefficient of the dopant, in this case, phosphorus, boron, arsenic, antimony. Diffusion coefficient or diffusivity, same thing. Diffusivity. Okay. So if you look at the graph here on the left, here is your surface x0, and then x is the depth into the silicon. Okay, sebelum ni kita ada silicon dioxide on top kan. So we will discuss about the linear and the parabolic mode of the oxidation. Let's just recall the flux coming into silicon dioxide before it reaches silicon for the interfacial reaction. Okay, sama. So here is the fixed law again. Okay, sama juga kita pakai untuk diffusion. Non-steady state situation, dopants continually diffuse. So we're going to learn about the equation shortly when we talk about the 2 different steps of diffusion. So when you run a diffusion, your profile, the profile, so this is the X, this is the N, this is the profile, this is the background doping. Horizontal is the background doping, waveform doping. We call it background doping or bulk concentration, same thing, but it belongs to the wafer. This one, the profile here, belongs to the dopant, okay, either it's p-type or n-type. So when you run the doping process, your dopant profile can take first one as one option number 1 can take complementary error function profile. The shape, the first case is complementary error function profile, and the second one is Gaussian profile. We're going to look into Gaussian profile later on. So your y-axis is the concentration, x is the depth, concentration at the surface is n0, nb is the background doping. So it can take, if you talk about complementary error function profile, you need to know the product of your dt of the process. Okay, dt product. So that means the product of your diffusivity times the time or the duration. Katalah process number 1 takes about 20 minutes. Process number 2 takes about 40 minutes. Process number 3 takes about 60 minutes, for example. And then at the same diffusivity, your D3T3 here, the product of DT will be more than your D2T2. It will be more than this. Okay. And D2T2 is more than the product of D1T1. Oh, sorry. D1T1. Okay. So because you run the process at longer time. So as a result, your profile goes deeper into the silicon if you run your diffusion process longer. Okay. Maksudnya kalau if you want to put this into silicon to compare, say this one is T1, this one is T2, this one is T3. T2 is longer than T2 is longer than T1, T3 is longer than T2, so T3 is the longest. So kalau you imagine this graph, it goes deeper into silicon, so that means your T1 may have depth of like that, your T2 may have depth of like that, your T3 may have depth like that. Okay, so that means your T3 has the deepest XJ or the junction depth if you compare to T2 and if you compare to T1. Okay. So your T1 has the shallowest junction because of the shortest time. You can also relate to this. So kalau nak tengok XJ, oops, the XJ for D1 T1, so that means you need to know this point. Okay, XJ, then D2 T2, XJ is here, D3 T3, XJ is here. Okay, so then the formula that you can use to calculate concentration and total dose are here. So kita akan tengok nanti macam mana nak guna equation ni. Right, the concentration is given by Nx equals to N0 error function. ERFC is the error function because you use error function profile for this particular case. Okay, and then error function of X is the depth over D times square root dt. D times square root diffusivity times duration of the process. Okay, so that will give you the concentration of the dopant at any point on the profile Nx. Okay, on the other hand, you can also calculate the dose or the amount, if you like, the amount of dopants you incorporate into the silicon. And that will be given by Q equals to 2 times N0, 2 times peak concentration times square root of dt over pi. Okay, dt diffusivity times duration of the process over pi. So N0 d error function is given here. Okay. Nanti kita akan tengok how do you use this equation to calculate the concentration and the total dose. So for example, so if you run this complementary error function, you can see that if you run the process at 15 minutes, 30 minutes, 60 minutes, right? 15 minutes, red one, blue one, sorry. 30 minutes, green one, 60 minutes, red one, right? So you can see that if you run the process using complementary error function profile, assuming you have error function profile, you will have your profile goes deeper into the silicon, right? Deeper into the silicon, but your N0 doesn't change. Your N0 doesn't change. So in this case, log concentration. So that's probably, your N0 is probably somewhere, say 7 times 18, for example. Every tak tukar, tak sampai 19 lagi, slightly below 19, okay, maybe 7 in 19, for example, E18, for example. And then, so now let's see, what is the junction depth for the 15-minute process? So let's see from the graph, and you can write down, you can unmute yourself. What is the junction depth of 15-minute process using complementary error function profile? Anyone? What is the XJ for 15 minutes? XJ15.
4.2.
4.2. How do you get 4.2?
At the end of the blue line.
Okay, how do you determine the junction depth? Okay, 4.2. Right? Any other answers? Okay. Amirul cakap 4.2 kan? Amirul tadi kan? Betul?
Ya betul.
Okay, any other answers? XJ15. XJ for 15 minutes. Macam mana kita determine? Alright, Faris said 3.5. Why 3.5, Faris? Unmute yourself. Kenapa 3.5? How did you get 3.5? Alright, so let's see here. Take the bulk concentration. Okay, then if you take the bulk, then the line there, okay, then how do you determine? Intercept between, habiskan jawapan tu. Intercept tu is very, intercept is hanging. Intercept of, depth and bulk, right? Intercept between depth, the depth of the profile and the bulk. So the intercept between your dopant profile, ya kena ni ya, habis explain accordingly. Kalau tidak, tak clear. Dopant profile, intercept of dopant profile, intercept dopant profile with bulk concentration. Tak benar? Sini. Right? And that brings you to 3.5 micron. Okay? Middle lah. So bukan hujung dia middle lah. Intercept between your bulk concentration. Ni wafer punya doping. And your dopant profile. So that brings you to 3.5. Right, so how about XJ30 now? How about XJ30? Sebab apa? Sebab apa? Oh, it has to be the intercept between dopant profile ni, intercept kat sini, and the bulk concentration. This is wafer concentration that we dope the wafer. Say your wafer is P-type and then your dopant is N-type. So your intersection between the two profiles come down here, right? Amiro? Okay, Amiro? Can you see this intersection point?
Oh, okay.
Kan? Straightforward, right? So how about XJ30 then? What is the XJ30? What is that junction depth? 4.9, yeah, about 4.9, right? 4.9, close to 5. Okay, 4.9. How about the last one, XJ60? Yeah, lebih kurang 6.9, right? Close to 7. Yeah, close to 7, right? So that's how you determine, very simple. Okay, notice that if you use complementary error function profile, if you increase the duration of the process, the junction goes into the silicon, or the profile goes into the silicon, leading to deeper junction. Okay, leading to the deeper junction, but your end knot doesn't change. Okay, end knot doesn't change. So kalau you jadi diffusion engineer, then this is your bread and butter later on. Tengok junction depth, then as a result your resistance. Ni pun kalau you buat, kalau you jadi engineer, process engineer for silicon solar cell, this will be your day in day out punya kerja lah. If you run diffusion, your junction depth, then as a result your sheet resistance will be following your junction depth, and then your recombination, your current, your voltage, your blue response, all the stuff will be derived from here. Okay, tapi ramai process engineer yang tak faham this concept sebab dia tak pernah belajar the junction depth punya konsep. Okay, bila dia dapat sheet resistance tu, kalau you kerja silicon solar cell ataupun some other solar cell punya business, dia dapat sheet resistance tu, dia tak boleh nak digest sheet resistance tu tinggi sebab apa, rendah sebab apa, in relation to junction depth. So bila you dapat deeper junction, saya tak relate to resistance lagi, tapi I just would like to give you a brief so that understand. So that's the beauty of learning physics down to this level. So bila you go to your you get deeper junction, maknanya you dope you punya ruang you dope dalam silicon tu lagi deep lah, lagi deep. So that will lead to lower resistance. Okay? Sebab you dope lagi dalam, maknanya you you embed more dopants deeper. If you measure the sheet resistance of the dope layer on the front, on the surface, that will give you a very low sheet resistance. Okay, so kita panggil dia RSH lah, R sheet resistance. So if you have deeper junction, your sheet resistance will be lower and lower and lower. If you have a very shallow junction, your sheet resistance will be higher. So if you relate this to solar industry, nanti you akan, if you go back to the EQE last time we learned quantum efficiency, carrier collection, all those stuff. If your sheet resistance is very low, and then your conductivity will be very good because it's the inverse of conductivity, and that will give you a high field factor. You punya squareness of the curve. You learned about 386 solar cell last time. The squareness of the curve, FF equals to Imax Vmax over IC VOC. So that will be very square because your resistance is low and your field factor is high. Okay, it's the inverse. On the other hand, if you dip a very shallow junction, your resistance will be very high because what? Let me ask you one question. Kenapa kalau you punya sheet is very thin, your resistance will be very high? Kalau you dope very thin, shallow junction, then your resistance will be very high. Sebab apa? Let's go back to 386. The device physics. Anyone can offer explanation to this? You dope very thin, shallow junction. Let me sketch here. Kenapa resistance dia tinggi? I discussed when we talk about carrier transport last time. So this is your P-type silicon wafer, then you dope N-type. Okay, katalah ni very thin layer. So that will result in high RSH. We not relate to device physics. Okay, kenapa kalau you dope very shallow, your shear resistance will be very high? Anyone? Anyone? Any guess? Can't remember? You don't have to remember. Anyone? Faris? What do you think? Kalau nak jadi device engineer, then you have to know this, okay? You have to relate the physics of the semiconductor with the device. What's the question again? All right. Why, when you have a shallow junction, as on my sketch, katalah dia too shallow lah, dia punya doping is very shallow. Your junction there is very small, or shallow junction, small shallow junction. Kalau XJ is very big, then deep junction. Kenapa kalau you punya junction is very shallow ataupun small XJ, your resistance, sheet resistance will be high? This is where it comes to the practice. Semiconductor physics dalam 386 now relate to the 487 in the process and eventually to the device operation in whatever device that uses the same concept of PN junction. Anything, Faris? Kavina? Yeah, think first. Kavina? Any opinion on this? No? All right. Alia? We're almost at the end of the first class. Someone? Alia, anything? Mac, anything, Mac? Saya dah explain dulu dalam 386. Kenapa kalau dia shallow ataupun dia punya dopant profile is very shallow or small, kenapa dia resistive? High shear resistance. Okay, alright, it's alright. Izati. So what is the majority carriers? Okay, let me see Faris. Small increase in bias voltage. Nope. Okay, what are the majority carriers in N-type? Okay, electrons. Okay, electrons. Good. Okay, let's go there now. So imagine yourself as an electron. You imagine diri you sebagai electron. Now you are driving. Electron driving. Katalah you are driving as an electron. And then imagine the the profile, the depth of the junction to as the root. Satu jalan XJ dia very small. Maknanya you jalan sempit. Then you have heavy traffic. Then satu lagi keadaan, if you have deeper junction, jalan besar, traffic yang sama, heavy traffic, but then jalan yang besar. So yang mana yang you senang nak gerak across? Kat mana yang senang nak jalan? Sebab jalan dia kecil, payah nak lalu ramai-ramai. Okay. Right. Kalau jalan kecil, susah nak lalu kan? You have the very same amount of traffic. Katalah you masuk Georgetown ataupun you masuk apa McAllister ke kat sana kan, air hitam. Selalu crowded, jalan kecil, lane kecil, kereta banyak, selalu jam. Right? The same traffic yang you experience in the narrow roads, you akan rasa macam susah nak drive kan? So that can be the analogy for the high shear resistance. Susah, jadi very crowded lah, right? On the other hand, kalau you ada the same amount of traffic, maknanya kereta sama aja, but instead of jalan tu jalan yang very small, narrow, you have a very wide road. Katalah jalan satu jalan tu, satu lane tu buat 3 kereta, tapi actually satu je yang drive on the lane, and you have the very same amount of traffic. It's a lot easier to move, right? It's a lot easier to move. So in that sense, the analogy corresponds to low resistance. Maknanya you nak drive pun tak perlu hati-hati sangat lah. Kan? Kalau you drive on jalan Scotland ke, kereta banyak, you memang kena tengok side mirror, motor lagi, foodpanda lagi kan. So you really have to be on the lane or within the lane so that you don't scratch each other or something. Tapi kalau jalan tu besar, you lebih relax driving, right? So that's the analogy. So you are the electron driving into the same path, into the same profile ataupun junction ataupun path. Junction yang hidup ni is actually correspond to roads lah, roads for carriers. Kalau N-type, electrons is majority, or P-type holes is the majority. So if you have a very shallow one, then it's going to be very, very resistive because it's going to be very packed, if you like, crowded, if you like, right? On the other hand, if it's big, deep, high XJ, then it's going to be less resistive. Okay, so that's why. So that's how you relate the semiconductor physics to the device physics. Okay, so if you talk about solar cell, then it goes to field factor efficiency. If you talk about MOSFET, then the drive current and all the stuff, right? So that's how you have to relate. Okay, let me continue with Gaussian profile, then we stop for a while. So that's the first one, error function. If you increase the process duration, the profile goes deeper into the silicon. As a result, your XJ increases. You're gonna end up with deeper junction, but your N naught doesn't change. Your N naught remains at the very same point on the y-axis. So surface peak concentration remains the same. On the other hand, if you use Gaussian profile, the second choice, saya kita tengok bila Gaussian, bila error function. So Gaussian profile is the second choice. So if you use Gaussian profile, so let's relate to dt1, t1, t1, d1, d2, t2, d3, t3. So note that if you use t1, for example, t1 in first name, so you're going to get that kind of profile. Okay. If you increase the process duration with the same diffusivity, so the profile goes deeper into silicon, just like error function, and your xj increases as well, just like error function. But you deplete the peak concentration of your dopant. Your N0 now reduces, N01 now reduces to N02. So if you use Gaussian, then you're going to experience the very same thing deeper into the silicon, but then your peak concentration reduces as you increase the process duration. So that means the amount of dopant supplied at the surface will be depleted over time. So if you run longer process, dia akan lagi depleted, jadi N03, N03, deeper. If you run D4, T4, for example, then it's going to take like that. It's going to be like that. It's going to be like that, right? So the N0 changes. Now, if you compare to error function, but the xj behave pretty much the same as what you get in error function, right? So the nx in this particular case is given by q over square root pi dt, right? Q is the dose you supply, dose of the dopant you supply on the surface. I'm exponential of this component, negative x over d times square root dt squared, right? And your n0 is given by this, diffusion coefficient and Gaussian profile. So that's the difference. So error function and Gaussian profile, similar, but they look slightly differently. We're going to use this for the calculation later on. So error function, okay, this is the error function profile, ERFC, or this, and this is the Gaussian profile. Okay, Gaussian profile. Okay, let's just stop here for a while. Then we'll try to finish the doping today. Okay, so any questions so far? Let's talk for about 10 minutes. Ada soalan so far? Is it okay? Is it clear so far? Okay ke? Paham ke? Right. Okay, so now it's 11 sharp. So let's continue at 11:10. Okay, continue 11:10. Huh? So I'll see you then. Bye. All right, let's continue. All right, can you see the slide on the screen? Nampak the slide on the screen? All right. Okay. Okay, so this is the diffusion coefficient of substitutional diffusers and interstitial diffusers. So just like what we discussed earlier on the substitutional and interstitial impurities. You can see the the diffusion coefficient is on the y-axis in centimeters squared per second, and the temperature, the inverse temperature, is on the x-axis, right? 1,000 over temperature in 1 over Kelvin, right? 1 over Kelvin. So on the left-hand side is the substitutional diffusers like boron, phosphorus, indium, gallium, arsenic, antimony, and aluminium. So on the other hand, on the right-hand side, you can see interstitial diffusers like iron, gold, copper, right, which can be dangerous to the device because they are deep level defects. That's what we discussed last time in phase 6. So if you compare, for example, if you compare the magnitude, okay, the magnitude between substitutional and interstitial diffusers, which one has the higher magnitude of the diffusivity or diffusion coefficient? Is it the substitutional or the interstitial? Which one has higher diffusion coefficient? Substitutional or the interstitial diffusers? John? Which one has higher diffusion coefficient? Left hand side or right hand side? Substitutional or interstitial? Go. Which one is the higher? Go. Which one has higher diffusion coefficient? For Kali? Which one is higher? Kali? Senyap ini? Right, interstitial, right? Interstitial. Graf mana satu? Dua-dua lah, dua-dua graf. Kiri substitutional, kanan interstitial. Which one is the higher? Interstitial, right? On the right, you can see the magnitude there. Okay, so see the magnitude on the right. On the right is 10 to the minus 5, 10 to the minus 6. And on the left is 10 to the minus 10, 10 to the minus 11. Way lower than the right hand side, isn't it? And if you look at the elements or the diffusers on the left, they are the intended impurities. They are dopants that you want to incorporate into silicon, which is fine. And on the other hand, if you look at the interstitial diffusers, they could be the unwanted impurities in the lattice, like copper, for example, lifetime killer. Okay, ataupun gold, for example, yang deep level defects, iron. Okay, but then they diffuse faster. So the higher diffusion coefficient means the diffusers diffuse faster into the lattice. Kalau faster, what happens if you run the process, or if you have your silicon with iron, for example, iron contaminants ataupun gold contaminants ataupun copper contaminants on the silicon, that will then go through high temperature processing in the fabrication process. So you akan diffuse dia lagi cepat lah, huh? You akan diffuse dia lagi cepat. So if you look at the x-axis there on both graphs, okay, katalah you tengok on the interstitial on the right hand side. So if you look at the both the graph on the right, for example, if you increase the temperature, so that means you are running your process to the left, right? Increase temperature, because it's the inverse of temperature, the x-axis. So look at the diffusion coefficient. So it's going to increase as well. It's going to increase as well. So if you look at copper, for example, at this point, say low temperature, if you go for high temperature, at that point, you can see the change in diffusivity or diffusion coefficient from 10 to the minus 7 to close to 10 to the minus 5. So it's like 2 orders of magnitude increase due to the increase in the temperature. So that will cause the diffusivity of the unwanted diffuser to be faster. And that will, of course, be dangerous for the silicon. Right. So diffusivity equals to D naught exponential EA over KT. This is Arrhenius relationship. Your EA is the activation energy, K Boltzmann constant, T is temperature, absolute temperature. And you can also see the summary of diffusion coefficient for a number of impurities. For example, here, the dopants and the unwanted in this case, all dopants, right? Boron, aluminium, gallium, indium, phosphorus, arsenic, and antimony. DT product is the measure of driving force in the diffusion. So that's why when you look into the graph just now, when you plot n against x, you can see that if you run your process with longer duration, you're supplying larger driving force. Okay, larger driving force that will drive the dopant into the silicon. Okay, DT is essentially the measure of driving force. You are giving more force if you increase the process time to the dopants to be diffused further into silicon. So D is proportional temperature. You can see in the previous graph, okay, D is proportional to temperature. Okay, higher temperature leads to higher D. Time at high concentration and high diffusion constant becomes dependent on the concentration. Okay, so when you run your diffusion process, the process can actually be divided into two steps. Okay, two steps. So the first one is called pre-dep and the second one is called drive-in. So you can either run your process with both steps, pre-dep, later drive-in, or you can just do either one. Okay. Okay. What is the meaning of pre-dep? Pre-dep means you're supplying the dopants onto the surface of silicon for a certain time at certain temperature. Okay. So this is called a step where you control the dose. You supply the dose Q. Q tadi dose kan? Q. Ada equation yang kita dah bincang tadi on the error function and on the Gaussian. Okay, so you're actually supplying the dopant gas or the dopant to the surface, right? In the next step, when you run drive in, you're actually turning off the dopant gas. You turn off the dopant gas or silicon oxide. Okay, maksudnya bila you run poker process macam tadi tu, furnace and you supply POCl3, during the pre-dep, you turn on the poker. You're supplying the POCl3 vapor into the tube for pre-dep, and then the moment you start your drive in, when you step, you turn off the POCl3 supply into the tube, but you just leave or you just run with whatever that you have, whatever dopant that you have on the surface. Okay, maksudnya bila you run pre-dep, you are constantly supplying the dopant gas. Tak kisahlah boron ke, phosphorus ke, whatever. You're supplying the gas at the same time while you are actually diffusing them into the silicon at the same time. But for drive-in, you stop the supply of the gas, so that means there's no new supply of the gas, so there's no new dopant coming into the tube, coming to the surface of silicon, but you just diffuse whatever that you have on the surface. Maknanya apa phosphorus yang ada, apa boron yang ada, you just drive it into the silicon based on whatever that you have only. Okay, there's no more gas coming in. If you notice, there's no more gas coming in. So this is the step where you control your profile, your junction depth, your concentration on the surface, and concentration into the silicon. So there's no new dopants supplied during the drive-in. Okay, so pre-dep by diffusion can also be replaced by shallow implantation step. Well, that can be done as well. Okay, so the essence of this step is pre-dep, you supply gas and actually diffuse it, forming the junction, a shallow one, into the silicon. Drive-in, gas supply stop, there's no more precursor coming in. You just drive tu maksudnya kita hantar ke dalam, diffuse ke dalam whatever that you have on the surface, right? So two-step diffusion process. The first step is called the error function, for example. Okay, the first step tadi tu, bila you run pre-dep, you're actually following the error function profile. So kalau you plot n against x, okay, n is the concentration of the impurity on the y-axis, and x is the depth of the profile into silicon. If you run pre-dep, you're actually following an error function profile, and this is the depth or the profile that you would normally have during a pre-dep. Okay, very shallow. The depth is like 0 point something micron, very shallow, depending on the process temperature and time. So that will be defined by your dt, A times T. Okay. So the moment you, okay, bila you run pre-dat, you are actually supplying the gas on the silicon. You supply the gas, the open gas. Is in, on. So bila you start your driving step, the second step, okay, tadi pre-dat as your first step. Bila you start your driving, it will take the Gaussian profile. So remember, the pre-dat will take error function profile, and the drive-in will take Gaussian profile. Okay, so with the drive-in, you don't have any more dopant gas coming into the tube, and there's no new supply of dopants. So you just drive whatever that you have on the surface into silicon. So that's why bila you buat drive-in, then you will notice that your peak concentration reduces from 1020 to 1018. So you are actually depleting what you have on the surface in order for you to drive them into the silicon. And when you do the drive-in, your depth increases. Okay, daripada sini say 0. I don't know, 0.1 perhaps. So now you punya junction depth is somewhere around 2.8. Contoh 2.8. Because that one is the background concentration. So wafer punya level kat sini. So your xj increases to 2.8 micron. So it was originally around 0.1 micron, around 0.1 when you do the pre-dap. And now the moment you've driven in the dopants into the silicon, your xj now becomes 2.8. And your N naught is depleted on the surface because it follows the Gaussian profile. Okay. So short high concentration constant source pre-diffusion approximate impulse dose at the surface. So pre-dap is where you supply the dose of your dopants, boron, phosphorus, whatever. You supply the Q to the surface. Longer drive-in step diffuses impurities into the lattice. You drive in the dopant into the silicon. So if you want to relate this to cross-section of silicon, say during a pre-dap, you may have your junction like that, a very shallow junction. On the other hand, when you finish your drive-in, you'll probably have something like that. Okay, so that's probably 0.1 micron, and this is 2.8 micron. Okay, after the drive-in. So if the dt for drive-in, if the dt for drive-in is much bigger than dt for pre-dap, then the final profile will be Gaussian. Okay, so we are actually following the Gaussian profile because the dt for drive-in is way bigger than the magnitude for dt of pre-dap, right? So if the dt for drive-in is much less than the dt for pre-dap, the final profile will be error function. Okay, rarely the case. If it really depends on the dt, and usually your dt for drive-in will be way bigger than the dt for pre-dap. So and that's why it will take the Gaussian profile for the drive-in. On the other hand, if the dt for the drive-in is way lesser than the dt for pre-dap, then your final profile, the drive-in profile, will take error function as well. Okay, will take error function, but that's rarely the case. Selalunya kita pakai Gaussian because the dt for driving will be way bigger because the temperature for driving will be a lot higher. Okay, say you might run your pre-dap at 700 degrees Celsius, for example, and then the moment you want to do your driving, your second step, you'll normally use 950, 1000. So higher temperature leads to higher diffusivity. Okay, kita tengok tadi kat previous graph, your D is proportional to T. If you run your process at high temperature, it will be diffusing faster into the lattice. Okay, so that's why your D is higher. So as a result, your DT will be higher as well if you compare to pre-dap. So is it clear? In terms of your two-step diffusion process, pre-dap versus drive-in? Before I continue, is it clear? Okay, clear? Ada yang tak faham? DT for predep, DT for driving, quotient, error function, junction depth. Okay, any questions so far? Nope. Clear? Right, clear. So let's move on. Solid solubility limit for dopant. Okay, there is a solid solubility limit to the amount of given impurity that can be dissolved in silicon. Okay, there's always an upper limit for the amount of dopant that can be dissolved in silicon, and that's called solid solubility limit of dopant. And it varies according to, it depends on the temperature of the process. Okay, if you run at higher temperature, then your impurity concentration, the limit will be higher. At high concentration, all of the impurities introduced to silicon will not be electrically active. Okay, so let's see this graph: arsenic, phosphorus, arsenic, electrically active. Okay, so let's see, for example, phosphorus. So let's look at phosphorus. When you incorporate your dopants into the lattice, not all of the dopants will be electrically active. And we discussed this one last time. When we talk about NP and S squared, remember the law of mass action. Okay, what was our assumption last time? Yeah, intrinsics. In order to calculate the majority and minority carriers and intrinsic concentration. Apa yang kita assume last time? Do you remember? N times P equal NS squared. Okay, what was our assumption with regards to the concentration of dopants? What was our assumption? Kita assume all the dopants are ionized, 100% ionized. Okay, 100% ionization. We assume 100% ionization. Maknanya apa yang kita incorporate into the silicon, say if you incorporate 5 times 10 to the 18 per centimeter cube, we are assuming that all the 5 times 10 to the 18 will be electrically ionized and they will be electrically active. In the real case, that's not the case. Okay, that's not the case. For example, in this case, if you talk about phosphorus, solubility limit of phosphorus, say at 1000 degrees Celsius, is like if you put somewhere there. So that's around 8 times 10 to 20, perhaps. Solubility limit of phosphorus at 1000 degrees Celsius in the silicon. But the amount of electrically active dopants, electrically active phosphorus, is only perhaps a logarithmic scale, right? So that's probably around 2, 3, yeah, about 3 times 10 to the 20, okay? So that means 3 times 3e20 versus 8e20 per centimeter cube. So electrically active is 3e20 and the solubility limit is 8e20, right? So that's a little bit of a reduction due to the non-electrically active dopants. Right, Xj is the metallurgical junction. We discussed this one just now and in the previous class as well. So for Gaussian profile, your Xj is given by 2 times square root of dt times ln n naught over nb. Okay, n naught over nb, nb is given, n naught is given. So if you know the chart, then you can easily calculate the junction depth. Is the dt information given. For error function, your xj will be given by a different formula, 2 times square dt, error function of n naught over nb. Okay, so p-n junction occurs when the net impurity concentration is 0, or pretty much the intersection between this and this. Okay, so ni pun lebih kurang kat sini lah, xj, right? So if you have your information given, dt is given, and then your n or nb is given, you can then calculate the junction depth of your Gaussian error function profiles, depending on which process are you using. Okay, for example, so let's test. So if you're running a pre-dep process, so which formula are you going to use in order to calculate your junction depth? Formula number 1 or formula number 2? If you're running a pre-dep process, you're required to calculate your xj. So will you be using formula 1 or formula number 2? You want? You're running pre-dep. Okay, Hazik said 1 Gaussian. Max said 1 Gaussian. Lagi, any other answers? You're running pre-dep process. You are required to calculate junction depth. Which formula will you be using? 1 Gaussian, second error function. Any other answers? So we've got 2 Gaussians. Sorry? How are you, sorry? Will you be going for the first one or second one to get your xj? Sorry, Izyani? Shafika? Alia 2, okay. Alia 2. Shafika? Amirul 2, okay. Juaria? So we have 2, 2 again. All right, 2. Okay, we have 2 voted for Gaussian. 1, 2, 3, 4. 4 voted for error function. Right. Why Gaussian? Why Gaussian? Mac and Haziq. Kenapa Gaussian? Oh, Haziq. Kenapa you pakai Gaussian? Why first formula? Teka je, mana boleh teka je. Kena ada sebab lah. You have to have reasoning. Mac. Why 1? Or why 2? Juaria, Shafika, Amirul, Alia. Kenapa 2? Why error function? What's your reasoning? Kenapa? Why Gaussian? Sorry, why Gaussian pula? Why error function? Sorry. Number 2, right? Why error function? Juaria? Kenapa error function? Okay, hold on. Let me see. Drive-in more than pre-dep. No, now you're running drive-in only. Pre-dep only. I mentioned pre-dep, right? You're running pre-dep process. I didn't say anything about drive-in. Kenapa 2? Sebab pre-dep, it takes error function. Pre-dep uses error function profile. Okay, go back to the previous slides. Tengok ni, yang kiri sekali ni, yang rapat dengan YZ ni. Pre-dep, it takes error function profiles, right? Okay, so that's why you have to use error function profile to calculate your xj, the second formula, right? Number 2, you cannot use Gaussian because it's not, it's a pre-dep process to begin with. Okay, unless you have a question that compares the dt of your drive-in versus pre-dep, then only you can use this. If the dt for drive-in is much less than dt for pre-dep, then you'll use error function. Or on the opposite case, Gaussian. Okay, kalau tak ada comparison, it's just a pre-depth, then it will take error function profile, which is equation number 2. So kalau you pakai xj daripada equation number 1, you will get different junction depth. Okay, because you are working on different equation. Right, clear? So let's move on to lateral diffusion. Let's try to finish this. Now 11:40. So when you run your diffusion process, if you compare to the earlier slide, bila kita compare diffusion versus implantation, we have seen that your diffusion profile tends to go inside and slightly wider, right? Slightly wider. On the other hand, if you talk about implantation, it will be at a certain depth, and then it will be more in control of the sites. Sebab dia lebih accurate. So your width control will be very accurate because you are bombarding the ions into silicon at a specific depth and width, right? On the other hand, if you run your diffusion, you will always have horizontal and a vertical component. Maksudnya kalau you need 3D, kalau you put that into 2D, say if this is the mask, we learn about silicon dioxide as the mask. Recall this, where you want to block the dopants from coming into the silicon if the thickness is thick enough to block. So you nak dope kat sini je. Say phosphorus coming into the silicon, you want to dope there. So when you do the doping by diffusion, you will have vertical component of diffusivity of the phosphorus, and at the same time you will also have lateral component, horizontal component. Lateral means horizontal. So that will lead to your profile being a little bit wider than intended. Right? And they can go on the side as well. So that's what you get here. Okay. That's what you're seeing here. Dia akan diffusion mass is the oxide. So the longer you go or the higher temperature you go, dia akan pergi ke side at the same time. Side. So it's quite hard to control because the lateral component or the horizontal component will always be there during the diffusion process. So if you talk about state-of-the-art technologies like 5 nanometer, 3 nanometer, 2 nanometer in the future, so you punya control will be very, very stringent, okay? So but you cannot afford to over diffuse, if you like, on the side because the dimension will be very, very critical. Okay, so at that point the profile control will be super critical for you not to introduce leakage current or something, right, on the diffusion profile. So you always have the profile for error function and also for Gaussian. Yeah, akan ada lateral component. Concentration dependent diffusion. Okay, the second law of diffusion, you can see the concentration dependent at impurity concentration and distance. And then this is the typical shape of the diffusion profile that you will see on the wafer. For example, after you diffuse, okay, so concentration is on the y-axis, depth of silicon is on the x-axis. So the process is run at 950 degrees Celsius. So you can see that if you run background doping at 2 times 10 to the 16 as your wafer doping, but then it's not reflected on the graph because it's way lower down here. 2 times 10 to the 16 will be down here. Ditunjuk sampai 1017 ya. 1016 will be here, then your background doping will be somewhere there, 2E16. Okay, for the wafer. So you can see the variation if you run the process for 10 minutes. So that's how the profile looks like. If you run at 20 minutes, it's going to go deeper into the silicon, just like the DT that we discussed before, right? It's going to go deeper. And then 30 minutes deeper, 60 minutes deeper. So if you extend this to the background doping, you'll probably get something like that, and then that will be there, XJ, 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 okay? So if your background doping is 1017, then your XJ will be here, there, right? So phosphorus diffusion is more complex, includes a kink ini apa? King ni dia punya ni, yang dia punya corner ni. Dia tak turun straight, ada corner, turun, ada macam tu. King, dia ada turn, a bit of soft turn. This is the king, so it's not like running, it's not like going like that. Tapi dia ada king. This is the king that we mean. Which makes it harder to use in actual devices. So that's why when you run your diffusion, you need to characterize the dopant profile. Okay, that's why kita discuss processing is always followed with characterization. Ataupun fabrication is always followed by characterization. You process, you need to characterize. You run your lithography, CED, you need to see your visual inspection, you need to characterize your overlay, you need to measure your CD, you need to, what else? Do the defect characterization. So that's why every processing has to be followed with characterization. Okay, so the same goes to doping process, diffusion process. Bila you dah diffuse, you then have to characterize the dopant profile in this case to understand what sort of profile are you getting. Are you getting the right one? Kalau you tak characterize the profile, you just measure the resistance, for example, and you may not understand if your resistance drifts. Say you are targeting 100 ohm per meters, 100 ohm per square, for example. Kata you target 100 ohm per square from this doping, then suddenly you are getting 120 ohm per square. Now you won't be able to tell why is it so, because what you see is only a figure. 100 as intended versus 120 is the actual result that you measured, but you don't know what's going on in the doping itself. So to be able to know why you have 20 ohm per square increase in the resistance, you need to go back to the doping profile, see what's going on. Is it following the profile as intended, or is it drifting to deeper into silicon or narrower because of certain behavior or something, right? You have to go back to the dopant profile, right? So let's try to finish in the next few minutes. I think I can get this done in the next few minutes. So resistivity versus doping, if you can recall, we discussed this in 386 last time. So when I mentioned that if you are given a silicon wafer with certain label, certain resistivity written on the box, for example. So let's just recap. If you're given a silicon wafer in a box, and then the box label resistivity of 1 ohm cm p-type wafer. So the question is, what is the doping level in the wafer? Okay, the label says resistivity of 1 ohm cm p-type silicon. So then you have to know the doping level inside the wafer before you process. So then what is the doping level inside the wafer in this case? Anyone? Can unmute and or write down. P-type 1 ohm cm. What is the doping level in the wafer that you get based on this curve? Anyone? Simple curve itu. Simple graph reading saja. It's nothing, it's not rocket science. Come, anyone? What doping do you have in your wafer?
Soalan dia apa tadi doktor? Saya tak faham sangat.
Okay, you are given a silicon wafer in a box dalam packaging. Dekat packaging tu is written the wafer has resistivity of 1 ohm cm.
Oh.
And the wafer is p-type. What is the doping level in the wafer that you have?
10, 16.
10?
10, 16.
And 16, right?
Yes.
Simple je soalan tu sebenarnya, okay? It's not rocket science. So 1 ohm cm, tengok graf ni je. 1 ohm cm. P-type ke N-type? P-type, right? P-type. Go to P-type. then go down. That's it. 1 times 10 to the 16. Okay. So kadang-kadang bila you dapat wafer, you don't know the doping level, but then other parameter is declared, which is resistivity. Tapi resistivity ini correspond to specific doping level. So what you have to do is come back to this curve and check. So on the other hand, if you're given, say, okay, let's try 10 ohm cm n-type. So what is the doping level in the wafer that you get? 10 ohm cm n-type. What is the doping level that you get? Ten ohm cm n-type. There, right? So that's like what? 6, 10, 15, or 6, 10, 14, sorry. 6 times 10 to 14. So my point is this, kadang-kadang you nak dapat satu information, but then the information is not given there directly, but instead something else is given. So you have to then relate to some other relationship that could connect your parameter to the another parameter. So this is always the case when you work later on. So it's not directly given there and then. Okay, you always have to use something to get something to be able to make decision. Okay, so to be able to understand the properties of the junction, okay, kita dah nak habis lah. Remember, processing is followed by characterization. So this is where you characterize your junction. So you have your p-type silicon, you have diffuse n-type into silicon, and you have a specific junction depth force from a certain process, for example, and you don't know what you get. So you have to use certain characterization in order to understand certain things or certain parameters. You can use ECV in order to characterize doping level and junction depth. Okay, ECV is electrochemical voltage characterization. ECV, you can check later on. You can also use SIMS, secondary ion mass spectroscopy, in order to measure both. Both here means doping level and junction depth. So you can know the doping level and you can know your XJ as well. Okay, you can also use Hall effect. We discussed in 386 last time. Okay, Hall effect can be used to measure doping level only. So you can only know your doping level is, say, 3 times 10 to the 17 on the surface, but you don't know the profile, you don't know the kinks, you don't know the depth exactly, right? You can pakai equation line to derive, but then you don't get to see visually what is the junction depth. But if you use ECV and SIMS, you can plot this. You can plot this kink kind of thing, X and against X. You can see the depth. You can then map to your substrate doping. You can then visually see the XJ. Tapi kalau you pakai effect, you need to put that into equation, derive, and you can get the number of XJ, but then you cannot visually see the XJ on the graph. But you can see the XJ on the graph visually by ECV and SIMS. Okay. So sheet resistance, we discussed on last time as well, R rho L over A. So sheet resistance is the resistance of the sheet. Sheet here means the channel that you're creating here, the profile here, the depth of the junction. So the sheet resistance of this thin sheet, yeah, narrow channel, jalan tadi, right? Sure. Sheet resistance is given by rho over T. Rho is the resistivity that you measured just now, and then if you know the thickness from the junction depth, xj is the T. So the T, if you have your rho, you divide by T, then you're going to have your ohm per square. That's why tadi saya cakap 100 ohm per square, 120 ohm per square. So this is the thing, it's RS. Kadang-kadang we call it as RSS, R sheet. Sebab RS ni kadang-kadang we use for series resistance in device. So that's why it's a bit confusing sometimes. So RSH is better used to denote sheet resistance, R sheet. Okay, RS typically R series, right? So doping system we have discussed. I don't want to go through. Okay, thermal budget is the last thing. Okay, when you run your diffusion, we discussed about thermal budget, right? Last time, when we talk about oxidation, the moment you run your process at high temperature process. So I'll finish in 2-3 minutes. you are actually imposing thermal budget to your products, to your device, to your chips, to your transistors, to your solar cell, whatever. Thermal budget. What is thermal budget? Thermal budget is, okay, dia akan ada high temperature effect to the properties of your profile, to your properties of your oxide, to your properties of your whatever. Okay, it's called by thermal budget. So in this case, since we are talking about diffusion, which forms the junction depth, the profile, the doping level, so dopants will be redistributed. Dopant will be redistributed when subject to various thermal cycle of IC processing step. So just remember, you run your pre-dep and then drive in at say 1000 degrees Celsius for certain temperature. So you've got your DT already, right? So you've got your diffusivity times your process duration due to your diffusion process. Tapi tiba-tiba, so after your diffusion, you've characterized, you've got your junction depth, you've got your profile, you've got your dopant concentration. Tiba-tiba your next process, you impose high temperature lagi. So that high temperature process in the next step is not intended for doping, tapi dia akan somehow disturb your doping profile or dopant junction depth or whatever, because it imposes thermal budget to the product, to the device. Okay, so if you talk about doping, then your dopant will be potentially redistributed when subjected to various thermal cycle. Next process high temperature lagi, next process high temperature lagi, so you end up changing partially or to some extent of your dopant profile, right? So if the diffusion constant at each step are independent of dopant concentration, the diffusion equation can be written as this. Okay, so you are actually imposing a new DT based on the new high temperature process. You run high temperature untuk anneal, for example, tapi bukan untuk dop pun. But then when you run at high temperature, you are actually altering the D for certain T, and that will impose a new DT to your process. DT, then the next DT, then the next DT, and the next DT, that will somehow alter the properties of your junction and the dopants. So that's why kita letak kat sini, dia ada DT, accumulated DT. So, and this is called thermal budget. Okay, for example, when we compare that to standard diffusion equation with D being time independent, we replace DT product in the standard, blah, blah. So consider a series of high temperature processing. You dah dope, and then you, in your subsequent step, you run high DT, high DT, high DT, you're imposing thermal budget, high temperature thermal processing cycle to the devices, to the material, to the transistor, to the products. So at temperature 1 times 1, temperature 2 times 2, and then you're imposing DT1, D1T1, D2T2. This is out of diffusion. Tapi dia, bila you run other process yang high temperature, dia akan impose DT as well, even though you don't supply the dopant at the same time. So if you like, it's like another unintended drive-in, sebab the gas dah tak masuk, tapi you run the process at high temperature that will correspond to certain level of diffusivity of the existing dopant in the silicon for certain time. So that will give you DT, D1T1, D2T2, blah, 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 accumulated DT. Okay. So the sum of DT products of these processes yang bukan diffusion ni, sum of DT product is sometimes referred to as thermal budget of the process. So dalam process flow tu you akan ada thermal budget introduced by processes that are not diffusion. Okay. For small dimension of IC devices, dopant redistribution has to be minimized, and we need low thermal budget processes. So if you're working on state-of-the-art technologies like 7532 nanometer, if you're continuously imposing high thermal budget process in the process flow of your IC fabrication, you're actually altering bits of your DT properties in your device. Okay, so you punya dopant profile mungkin start off something. If you plot dopant profile, it probably be something like that. If you plot an X after the diffusion, if you run ECV to characterize, then you may get something like this. Tapi bila you impose another process yang tak intend to change the dopant profile, but somehow will change the dopant profile, that will probably be something like this. Your new dopant profile will probably be something like that. Okay, or probably be something like that. But you don't know this because is not meant to be changed in the first place, but it does change the process. It does change the properties of the dopant. So this change may alter your overall sheet resistance, conductivity, resistivity, dopant profile, peak concentration after accumulated DT. Okay, so that is called thermal budget. So you don't want to have it, but you don't have a choice because you need to run your subsequent processing at high temperature as well, or else it won't do the job. Because later on you're going to learn about annealing that will repair defects and all the stuff that will repair crystal lattice after ion implantation, for example, which requires high temperature processing that will inevitably impose accumulated DTs to your products, right? Okay, so thermal budget, for example, in summary graphically, temperature over time against time. So this is your driving step that you intend to impose to your device, but then you have to anneal in the next step. High temperature juga, so you impose another DT as well. So that will perhaps alter the overall DT, the effective DT of your device due to this accumulated DT. Okay. So for a complete process flow, only those steps with high DT values are important. That will affect the DT of the final devices. Okay. You run next process at low temperature, so that will not impose any thermal budget to the device or to the products. Right, so these are the questions that I want you to try. We can discuss later on. Try this pre-depth and try the equations and try to calculate the junction depth. We'll probably discuss this sometimes next week when we talk about before we talk about ion implantation next Monday. Okay. So is it okay so far? Done? We're done with the second session. 12 already. Is it okay? Can you follow? So we finished diffusion today. Habis lah diffusion. Next, we're going to discuss ion implantation, another way to dope your silicon. Okay, and then we're going to move on to thin film deposition. Sekarang dah week apa? Week 10 kan? Okay. So, is it week 10 or week 8? Week 9 ke week 10 sekarang? Week 10 kan? Lupa lah. Okay. Week 10, right? Week 10. Already, so fast. Okay, so try to attempt this question, yeah? 1 and 2, using the equation that we discussed, pre-depth or drive-in. See which one is appropriate for which condition. And then we're going to discuss the answers Monday, next week, inshallah. So if there's no question, then I'll see you next week. Bye-bye. Take care. Assalamu alaikum.